So good morning, and let's tackle about the atomic spectroscopy. So atomic spectroscopy is like a fingerprinting technique for atoms. Just like every person has a unique fingerprint. So every type of atom has a unique pattern of light. So there are two types of techniques, the atomic absorption spectroscopy and the atomic emission spectroscopy. And these techniques are of utmost importance because of their ability to detect even the trace amount of elements in a very small amount of sample. Now, like for example, is testing drinking water. So, a city wants to make sure if ilahang water is safe ba to drink. So, they take samples and want to check for any harmful metals nga naa dito sa water. So, using the atomic absorption spectroscopy, they shine light through the water samples by measuring how much light is absorbed at a specific wavelength. So, they can figure out if there are metals like lead or mercury nga present dito. So, if they find out, they can take steps to clean the water or warn people about it. So, the atomic spectroscopy no makahelp gyud siya to keep the water safe from for everyone to drink. Okay, that's it. Thank you.
Atomic spectroscopy. Atomization is the process of converting an analyte to a free gaseous atom. In ASS, we want to analyze the elemental composition of a sample, but the sample are often in a liquid form with the elements dissolved in water or the aqueous solution. So atomization is the crucial step or the crucial part that converts the analyte from its dissolved state in the liquid to free gaseous atoms. There are a few key things happening during atomization process of an aqueous analyte. First, solvent removal or the dissolution. So we need to get rid of the water surrounding the analyte. So this is typically done by heating the solution, which causes the water to evaporate. Yes. Second, volatilization. Once the water is gone, we need to vaporize the analyte itself. So this often requires even higher temperature than those used for dissolution. So not all elements vaporize easily, and some may decompose into different compounds before reaching the gaseous state. 3. Dissociation if necessary. So in some cases, the analyte molecules might need to be broken apart into its constituent atoms. For instance, in our example, the CuCl2 or the copper chloride, the molecule needs to be split into individual, the copper and the chlorine atoms. So this is the chemical equation provided, and it is nicely illustrated this process for CuCl2. So kani akong gi-present sa atong PowerPoint ang example. So the CuCl2 AQ or aqueous represent the copper chloride analyte dissolved in water or the aqueous solution. Muna siya itong aqueous solution. The CuCl2 or S represent the solid copper chloride formed after the water evaporates. So the CuG and ClG represent the final product or the free gaseous copper and chlorine atoms. So with that, there are different atomization techniques. There are different methods to achieve atomization. And the choice depends on the specific analysis. Here are two common techniques. There are two common atomization methods, the flame atomization and the electrothermal atomization. So first, the flame atomization. So the sample solution is nebulized or turned into a fine mist and mixed with a combustible gas. So the mixture is then burned in a flame, which provide the energy for dissolution, volatilization, and dissociation. Okay, so mao to siya ang flame atomization. But then, dili man ako mapakita sa inyo ang ilahang function, kay nagamit sila og instrument. O kaning picture nga naa sa atong PowerPoint, muna siya ang amo ang nakita dito sa PDF nga gihatag sa amo ani mga baby. But then nag-research ko og kanang instrument kay ani, pero wala na kay ko nakita. It's because old model na siya, kay nagamit ni siya according dire sa atoang sa amo ang gibasean sa PDF kay 1970s ni siya nga model. So sa ako ang pag-research na ako yung mga nakita nga model nga same function but different model na, kay nag-evolve naman ta. So lahi na ang kuan, mas unique ug mas dali kay didto kay naka-connect na siya sa computer which is moto siya ang mo kuha sa mga data nga inyohang gigamitan ana nga instruments. Kani nga part mag-present ko og duha ka video, ipakita dire ang iyahang process, ang mga example, unsay mga buhaton, iyahang mga parts ana. So together kamo nga naminaw og ako nga reporter mag-learn ta nga dungan ani nga video sa maminaw og tarong og maglantaw og tarong. Okay?
My name is Catherine and I'm going to be taking you through the atomic absorption spectrometer. This instrument is provided by Varian and its model is an AA240. So we're going to have a look at how we can actually atomize a sample and then see its absorbance. So the first part of this type of analysis is to introduce the sample into the system, and that's done using this fine capillary tube. So our sample will be drawn up into this capillary tube and it's going to make its way into the nebulizer. So if I just pull this heat guard off, have a clear look at what's going on in here. So sample is drawn into the capillary tube and this white section here is called the nebulizer. And this is where the sample that's already in a mist becomes an even finer mist, a very, very fine spray of droplets of your solution containing your sample, the metals. Those droplets are created by the nebulizer, are moved using carrier gases into this burner slot, which is where the flame is. So the gases have two roles. Their first role is to sweep your sample of droplets into the flame, and secondly, once they're in the flame, to act as a fuel, so that our flame happens at very, very high temperatures, over 1,000 degrees and above, depending on the mixture of gases that we use. Once our sample gets into our flame, three different things happen. First is desolvation, and all that means is that the solvent that's used to dissolve our sample is burnt off, so we're left with compounds. And then the compounds break down or decompose because of the really high temperatures, and then we have free atoms and ions which are up there in our flame. At this point, a light is shone through the base of the flame, and this is where we can get excitation of electrons that are within the atom or ion that we're interested in looking at. And this light comes from a hollow cathode lamp. Over here in this section of the instrument, we have a range of hollow cathode lamps. Now in your textbooks you might have seen some instruments and they just have one hollow cathode lamp. The lamp is specific for different elements. So for instance, this top lamp we use for calcium, magnesium or aluminium metals. So our light will be generated from this lamp at set wavelengths and will then be able to pass through our sample. So at the moment what we will have is a range of different atoms and ions burning in our flame. And as we pass the light through, that light is specific for a particular element. So if I was looking for magnesium, a specific wavelength of light is going to be passing through my flame. Any magnesium atoms will be excited, their electrons will be excited to a higher energy level. And then, as they return to their ground state, they'll give off that energy in the form of photons of light. So what will happen is these photons of light will pass through to the detector, which is in this part of the instrument. And the instrument will actually be able to see an increase in the amount of light that's transmitted between what comes through normally and when you put a sample in, extra light's going to be given off. And that's converted to a function of absorbance. And so we can use an AAS to determine what's present in our sample. So if I'm looking for magnesium, if there's any magnesium present, and secondly, how much is present by how much light or energy is being absorbed.
This animation of a flame spectrophotometer will provide an idea of how the machine works. The analyte is taken into the nebulizer where it is vaporized and conditioned to provide the best sample for the flame. The radiation source sends light through the flame and into the monochromator. In the monochromator, the beam encounters a series of mirrors that separate the beam from any background light and noise that is not necessary for analysis. This filtered beam finally hits the detector, which relays the data to the analysis software. This is the gas that feeds the flame. These are the lamps that provide the source of radiation. The lamp is specific to the analyte. The analyte is taken into the flame by this capillary tube. Data collection is performed by software installed on a computer. This demonstration will use a sample of copper. First, start by cleaning the sample capillary with a chem wipe. Then, insert it back into the sample to be aerosolized, mixed with gases, and released into the flame. The flame turns a green color that is distinctive of copper. Waste is then siphoned off into a collection bucket. The data is then sent to the computer for analysis.
Okay, so moauto siya ang flame atomization, and I hope nga naka-learn mo dito sa video nga akong gipakita sa inyo. Okay? So the flame's temperature, which affects the efficiency of atomization, depends on the fuel-oxidant mixture. So the sample introduction, the most common means of introducing a sample into a flame atomizer is a continuous aspiration in which the sample flows through the burner while we monitor absorbance. So continuous aspiration is a sample intensively, typically requiring for 2 to 5 ml of sample. So makita diri sa ato ang table ang fuel o yang oxidant o ang flame nga or ang temperature range niya. So for example, the natural gas, iyang oxidant is air, and the temperature range around 1700 to 1900. And for the fuel, hydrogen, yang oxidant is again air, and yang temperature range nagkataas, which is the 2000 around 2000 to 2100. Ang yang acetylene, air ang oxidant, and yang temperature range is 2100 to 2400. Then acetylene again, yang nitrous oxide, ang iyang temperature range around 2600 to 2800. Okay? And last, the acetylene, ang iyang oxidant, oxygen, and the temperature range is 3050 to 3150. Okay, next, the electrothermal atomizer. A significant improvement in sensitivity is achieved by using the resistive heating of a graphite tube in a place of flame. A typical electrothermal atomizer, also known as a graphite furnace, consists of a cylindrical graphite tube approximately 1 to 3 cm in length and 3 to 8 mm in diameter. So this electrothermal atomization is a small amount of the sample solution is deposited in a graphite furnace. The furnace applies a program of increasing temperatures to achieve the required step of drying, ashing, or decomposition of some of the matrix and atomization. So imagine you have a tiny sample like a drop of blood that you want to analyze to see what metals are in it and how much of each metal there is. An electrothermal atomizer helps turn that liquid sample into a vapor cloud made up of individual atoms. So here's the key different from other methods. Instead of the using a flame which is hot but can't be messy and not very precise, an electrothermal atomizer uses electricity. It has a small hollow cylinder made of graphite, a form of carbon that conducts electricity well. When you run an electric current through the graphite tube, it heats up tremendously like a tiny oven. So the sample is injected this hot graphite tube. So the heat from the tube first gently dries the sample, like removing the water from a puddle. Then the temperature goes even higher, burning off any organic molecules in the sample. So finally, the temperature gets very hot enough to vaporize the metals in the sample and turn them into individual atoms. So this cloud of atoms is what the instrument can then analyze to figure out which element are there and how much of each. So using an electrothermal atomizer has two main advantage. Super sensitive because the heating is very efficient and contained. It can turn nearly all the sample into atoms. This means the instrument can detect even very small amounts of metal in the sample. Second, the cleaner analysis. The high temperature can break down some molecules that might otherwise interfere with the analysis, making the result more accurate. Okay, next, the miscellaneous atomization method. So in science, sometimes we want to study individual atoms of an element, but getting them to separate can be tricky. So there's where atomization comes in. It's like breaking apart a crowd to see each person clearly. So most atomization methods involves high heat, but there's special techniques for some shy elements. So this is called the miscellaneous atomization method. So imagine you have elements like arsenic, selenium, or lead. These guys normally don't like being alone as atoms, but with a little chemistry, we can convince them to form a temporary team up with hydrogen. So hydrogen, a volatile compound called a hydride. So here's the secret weapon, a chemical called sodium borohydride or the NaBH4. Kind of a matchmaker for atoms. So when we add NaBH4 in an acidic solution, it reacts with this element, so creating their volatile hydride partners. So think of it like this. The element is like an introvert who prefers to be with others. Hydrogen is a friendly gas, allows willing to bond with others. So the NaBH4 is the party planner, introducing the element and hydrogen so they can form a temporary hydride bond. So this hydride is special because it readily evaporates, becoming a gas. We can then carry this gas with an inert gas like helium into a hot flame or a heated tube. So inside the hot zone, the hydride breaks apart, finally releasing our element as free individual atoms. So by using a clever chemical reaction, we can turn these tricky elements into cooperative hydrides, separate them as a gas, and then break them apart to see them as single atoms, ready for further analysis. So that concludes our exploration of atomic spectroscopy. Now let's move on to the next topic, which is build up upon this knowledge about quantitative application.
Moving on, thank you so much. Next is the quantitative application of atomic absorption method. So as we all know, developing an analysis in analytical chemistry requires different criteria, protocols that we must adhere in order for that to be accepted. Now, just like that, in development of a quantitative atomic absorption, of course, it requires several criteria as well, and one of which is the choice of atomization and citation sources. Why do we need to atomize our sample? Because atomic absorption analysis will not work if ang atoms o ang molecules sa ato ang sample kay dili on its excited state. So there are so many apparatus that carries out the excitation transition of a sample, and one of which is it's either a flame or electrothermal source of atomization. Now, the appropriate tool that carries out the atomization and the excitation of our sample depends on the concentration of our sample. For example, if ang element is aluminum and ang concentration sa atong sample is 40 milligram per liter, then we are going to use flame atomization. On the other hand, if the concentration of our sample is 0.050, then ang gamiton nga apparatus is electrothermal atomization. So it's always the choice of atomization and excitation sources will always depend on the concentration of the analyte in our sample. Next, selecting the wavelength and speed. In here, we are going to select an apparatus that carries out as a radiation sources when it comes to selecting the wavelength and speed of a sample. We must always bear in mind that atomic absorption line is about 0.02 nanometer. In line with that, we are going to select apparatus that is narrower from that atomic absorption line. And why do we need to use narrower? It is because if we're going to continue utilizing continuous radiation sources, it is difficult for us to detect absorption, which results from incident radiation at all. And if we are going to use continuous radiation sources, narrow ang iyahang slit. If narrow ang iyahang slit, then there is a tendency na lower ang iyahang sensitivity. If it is lower sensitivity, then it is expected that we are going to have an interference which affect the accuracy of our analysis. That is why always bear in mind that in selecting the wavelength and slit sources, we have to use those radiation sources that is narrower from the atomic absorption lines. And one of the apparatus that is narrower from the atomic absorption line is the cathode halo lamp. This one, what is a cathode halo lamp? It is composed of a cathode that carries negative ions and anodes that carries positive ions, which is separated from another glass tube. This cathode lamp is an alloy that is made up of manganese, copper, nickel, and chromium element. We are going to assess under these elements, we are going to use this cathode halo lamp. So if there is an interaction between the negative ions and the positive ions, then there is a sputtering that occurs, and mo ni siya ang ato ang i-assess. So this sputtering are going to assess that we're going to assess the wavelength and the speed of that sputtering process. Next, preparation of the sample. When it comes to the preparation of the sample, it depends on the atomization that we are going to choose, because flame or electrothermal requires the analyte to be in a liquid state. So if our sample is in a solid state, we must dissolve it into its appropriate solvent with the use of a hot plate or being put in a microwave that is being applied by a nitric acid or a peroxynitric acid. After which the liquid sample will then analyzed and undergone the chosen atomization method, depending on whether those methods are applicable or compatible to the chosen sample. Next, we have another criteria that we are going to consider is minimizing the interferences that occurs in our analysis. The atomic absorption method has a various interferences if our method is not accurate at all, and one of the interferences is the spectral and chemical interferences. Now, how does this two occurs? Spectral interferences occurs if first mag-overlap ang atomic absorption line and interferences line during the selection of wavelength and slit width. That is why I emphasized a while ago that there is a must to carefully choose our apparatus that carries out radiation sources. Next, it occurs especially if during sputtering process, yung collision of yung collision of ions in cathode and anode, our cathode hollow duct. And lastly, it occurs, spectral interferences occurs if our sample produces another molecular species in an atomic absorption method, such as oxides and hydroxides. How do we be able to minimize spectral interferences? First, I already mentioned it a while ago that we must choose an apparatus that is narrower to the absorption line, which is about 0.02 nanometer. Second, if we are just going to know keenly if kabaluta unsa ang composition sa ato ang samples matrix, then we are going to produce an identical sample matrix that is identical to the results if we are going to test under atomic absorption method. If we are just keen to the composition of our samples matrix, then we are able to adjust the atomization of our samples. Kabaluta mag-adjust sa atomization process if increase ba nato or i-decrease ang temperature to eliminate interferences. And third is ma-minimize nato ang spectral interferences if magamit ta og flame or atomization, especially when it comes to increasing the temperature because it avoids the production of another molecular species such as oxides and hydroxides. And last but not the least is the usage of the application of a method which is the background correction, especially the utilization of a continuous source like T2 DAP. That is how we minimize spectral interferences. Next, chemical interferences. That's, of course, during atomization. The most common chemical interferences is the formation of non-volatile compounds. Now, how do we be able to minimize chemical interferences? First is the utilization of flame atomization, especially when we are going to increase the temperature of the atomization method. Another approach that we can use to minimize chemical interferences is the application of releasing agent and protecting agent. The releasing agent is the species that interacts preferentially with the interferences, releasing the analyte during the atomization from the interferences. On the other hand, when we talk about protecting agent, this is the species that interacts with the analyte, which creates a much more stable compound. So those are the methods in order for us to minimize chemical interferences during atomic absorption analysis or method. After the development of our atomic absorption spectroscopy method, of course, we have to evaluate whether it is appropriate when it comes to the scale of operation, accuracy, precision, selectivity, sensitivity, time, cost, and equipment. When it comes to scale of operation, ideally, atomic spectroscopy method is used for the analysis of trace and ultra-trace analytes. Specifically, it is used to trace elements in a concentration of elements in a specific sample. So for a minor and major analytes, it is first diluted before analysis because usually the concentration that is appropriate under atomic spectroscopy is meso and macro samples. Next, we have accuracy. The accepted or the attainable accuracy value is just 0.5 to 5% only. That is the accuracy. Next, when it comes to precision, for the absorbance greater than 0.1 to 0.2, the relative standard deviation for the flame atomization is 0.8 to 1%. On the other hand, for electrothermal atomization, we have 1 to 5% of precision when it comes to the relative standard deviation. Next, we have sensitivity. So, the sensitivity of atomic absorption spectroscopy varies on the atomization method that is used. For flame atomic spectroscopy, the sensitivity is influenced with the flame's composition and the position of flames itself. Well, we can optimize this by adjusting the temperature of the flame or increasing the temperature of the flame. Next, when it comes to the electrothermal spectroscopy is influenced by the drying or the ashing stage which precedes to the atomization. You can optimize this with by adjusting the temperature as well, just like the flame atomization, and also the time at each stage occurs. Aside from that, the sensitivity of our atomic spectroscopy method is influenced with the samples matrix as well. We can optimize this by adding a lower molecular weight of alcohol, ether, or ketone. So in that way, we can optimize the sensitivity when it comes to the samples matrix composition. Next, when it comes to selectivity, the atomic absorption spectroscopy method is used to analyze for about 60 elements with a concentration below or at the level of micrograms per liter. Next, the time, cost, and equipment. The analysis time of flame atomization is much more shorter compared to electrothermal atomization, which has about the analysis time of flame atomization is much more shorter with a sample throughputs of 230 to 350 determination per hour. On the other hand, electrothermal atomization has 20 to 30 determination per hour, which of which is much more affordable. Well, flame atomization is much more affordable compared to electrothermal atomization. That is why I mentioned a while ago, I already emphasized that we have to evaluate carefully to develop atomic absorption spectroscopy, not just by the sensitivity criteria, but all of the criteria that I had already mentioned a while ago. I guess that's the end of my discussion. I hope that you had learned something because we had discussed the concepts, ideas, and information behind spectroscopy. Hashtag we really do love analytical chemistry. But before leaving, I will share with you a quotation. According to Frederick's body, chemistry is easier if you happen to love with it, but it is harder if you happen to crack with it. Which means that all we have to do is just to love chemistry because at the end of the day, we realize that it's easier for us to understand the concepts. Once again, thank you so much, and God bless us all.